mathematical induction. Very useful technique in proving a statement involving integers. So math, usually because we are doing mathematics, we simply say induction. Mathematical induction. It means mathematical induction in my class. The induction is a proof technique to prove a statement like this. For all n positive integer, S of n, property. For all n S of n, this is a proposition that we want to show. And we show this by showing the following two things. First, we show that S1 is true. And this is called a basis case or basis step. And second, we show that for all n, at least 1, if Sn is true, then Sn plus 1 is also true. So this statement, if you look at this, says that S of n is true for all integers, all positive integers. But how many positive integers are there? Infinitely many. You cannot count them. So you cannot prove this by using the technique called proof by cases, because you cannot list all the positive integers. They are infinite. But instead of doing that, but there is a kind of a way to check all integers. But that is this. You show that the S1 is true, and you show that if Sn is true, Sn plus 1 is also true. If you show these two things, then what happens is S1 is true, right? Suppose that these are true. By the basis, this is called induction step, by the way. Because of the basis step, we know that S1 is true, right? And because of the induction step, we know that S2 is true, because S1 is true, 1 plus 1, 2 is also true. Because of this, again, S3 is true. Because of this, S4 is true. We can go just forever. So for any integer n, Sn is true because of these two things. So if you show these two things, then that means you showed all S of n is true for all integer, positive n. So very useful and powerful technique, because you don't have to check all the infinite cases. Just two things are enough. Let me give you an example of this. Yeah, I think you have seen this kind of thing very often, but yeah. Let's say, before doing that, let me define one thing. It's an integer, I0 integer, at least 0, so meaning non-negative integer. N factorial is defined to be either 1 or 1 times 2 times n, if n equals 0, if n is greater than or equal to 1. So n factorial is basically the product of integers 1, 2, 3 up to n. But 0 factorial is defined to be 1. And 1 factorial is 1. 2 factorial is 1 times 2 equals 2. 3 factorial, 1 times 2 times 3 is 6, something like that. Do you think this is reasonable to define n factorial to be 1? Why is this? Why should we define 0 factorial equals 1? Somebody maybe want to define like this, right? I'm telling you, in definition, people say that you have freedom in mathematics. That means you can define anything as you wish. If you want to define this, that's fine, as long as you don't have any contradiction. But that's fine. It's like a language. If you create your own language so that no one can speak that language, that's fine. You don't speak Korean, Japanese, English. You create something very strange language just for yourself. That is fine. This is like that. The problem is you cannot communicate with other people. You can define this, but the problem is there are not many people who use this definition. So you cannot communicate with other people because most people would use this. But there is a good reason to define n factorial to be 1, because n factorial means 1 times 2 times. You multiply things, but starting from what? Do you start from 0? If you start from 0 and multiply things, then you always get 0. So 0 factorial means you don't multiply anything. So you begin with the first thing, or things that has nothing in terms of multiplication, which is 1. So that's one way why people like to define this to be 1. But like I said, it's fine to define whatever value you want this to be, but many people define this way. It's not very important, but yeah, I just want to understand that math has some freedom in it. Anyway, we know what this factorial is. So now let's prove this. Prove n factorial greater than or equal to 2 to the n minus 1. Actually, n factorial grows very, very quickly. This one also grows very quickly, but even quicker than this. For all n greater than or equal to 1. Yeah, proof. Induction. Usually in induction we use, because this is the first time, let me try to write everything in a full sentence. We use induction on n. We are going to use induction on n. So basis step, n equals 1. Let's check if this is true. 1 factorial, is this equal to 2 to the 0? What is 2 to the 0th power? 1. This is 1. 1 greater than or equal to 1. It's true. So we have checked that the basis step is true. And inductive step. So we assume that this is true for n. Suppose that the statement is true. True for n greater than or equal to 1. Now we want to show that it is also true for the statement with n plus 1. So this means we are assuming that this is true. The statement meaning this. Now we want to show that if you replace n by n plus 1 here, the statement with n plus 1 is also true. So n plus 1 case, we want to show that this is greater than or equal to 2 to the n. But we know by definition of this, n plus 1 times n factorial, right? This is the definition of this follows from the definition of the factorial. And now what? Okay. And here, by induction hypothesis, n factorial here, n factorial is greater than or equal to 2 to the n minus 1. Because we are assuming this. We assume this. If you assume this, you want to use this. Otherwise, there's no need to use induction. Now, what is n plus 1? So here, n plus 1 factorial, n plus 1 factorial, n plus 1, n factorial. By this, greater than or equal to n plus 1 times 2 to the n minus 1, right? I just use this fact. Now, what is n? N is at least 1, so n plus 1 is greater than or equal to 2. So this will be greater than or equal to 2 to the n. But if you look at this thing over here, we have just shown that n plus 1 factorial is greater than or equal to 2 to the n. But if you really look at this, then in other words, is it greater than or equal to, okay, let's write this. Greater than or equal to 2 to the, this one is n plus 1 minus 1 if you want. So this statement, the same statement is also true for n replaced by n plus 1, right? This means the statement is also true for n plus 1, because that's what this means. And by induction, it is true for all n. This is the end of the proof. So you prove a statement involving integers like this, positive integers like this. There are many, many examples that you can use mathematical induction. So whenever you have a statement involving positive integers n, the first thing that you can think of is to use mathematical induction, because it's very, very powerful. Things can be proved very quick, very easily, and just routine, in a routine way. Is it okay? Induction? All right, now we are going to, if we have time at the end, we will see more examples of this induction, but let's move on to the next section. It's basically induction, but strong form. Of, wait a second. Okay, yeah, before doing this, sorry about this. Let me tell you a little variation of an induction, but basically they are the same. If you look at this, I told you that this is a statement for all n greater than or equal to 1. But you can also, there can be a statement for which n is at least 5 or something, not 1. You can still use induction like this. All you need to do is this. So if we want to show that for all n greater than or equal to n0, for fixed n0, s of n, instead of 1, before we had 1, all n greater than or equal to 1. But this can be any number, like even negative number. N greater than or equal to minus 5 or n greater than or equal to 12, something like that, you can still use induction. We can use induction in this way. So basis step, only the basis step changes. Instead of showing s of 1, you just show s of 0. That's it. And induction step is the same. It's the same. If Sn is true, then Sn plus 1 is also true. If you show these two things, then you have shown this for all integers greater than or equal to n0. Doesn't have to be 1 always. Because sometimes Fn may not be true for n1 or 2. There can be some examples that it's not true. But at some point, if this is true after some numbers, then you can use this kind of induction. Okay? Now, really the next section. The strong form induction and the well ordering property. Okay, so strong form of induction is kind of similar induction. So a strong form of induction, or just simply say, let's say strong induction, is a proof technique to prove something like this. For n, at least n0, like the fixed integer n0, s of n, by showing the following. The two things. Basis step. The basis step is the same. Sn is true. You show that this is true. The first number is true. Second, inductive step. Inductive step. If Sk is true for all k between n0 strictly less than n, then Sn is also true. If you show these two things, then you have shown for all integers n greater than or equal to n0. So it's slightly different. Let's compare this with the usual induction. I'm sure that you are familiar with this usual induction. So maybe you have seen this for the first time. If this is your first time to see this strong induction, you may want to compare with the usual induction. Induction and strong induction. Let's compare these two. Just using some kind of diagram. So in this induction, what we do is we show that n0 is true. Okay, let's write this. n plus 1. What we show is that, let's say basis steps are the same. So induction step, inductive step, this, okay. We show that if this is true, then this is also true. This is what we do in induction, usual induction, right? We show this thing, and then we show this inductive step. If n is true, n plus 1 is also true. On the other hand, in the strong induction, we have the same set of integers that we want to show. But yeah, here I used n, but let's use n plus 1 just to compare this. Here, we assume only this in this usual induction. We only assume s of n, and we derive that Sn plus 1 is also true. But here, we assume not only one s of n, we assume all of this. Sn0 is true, Sn0 plus 1 is true, Sn0 plus 2 is true, all the way up to S of n. Then we conclude that by using all of this, or some of this, we conclude that this is also true. So that means we have more assumption in our inductive step. That's the difference. That's the difference of the induction and the strong induction. We assume more, and then we prove this. It's the same that we want to show the next element, but in the strong element, strong induction, we only assume the previous case, but we assume all of these cases. And do you think why this is called strong induction? Because it's in some sense stronger than the induction. This can be used to prove something that may not be proved using induction by itself. It is strong because it has more assumptions. You assume more things. What does it mean that you have more assumptions? you can use many things. Because when you prove something, you use assumptions. If you have many things, that means you can use many of this. Not only this, but also this. So this, if you can show something using induction, that can always be showed using strong induction. But the opposite is not the case. So if you don't know what to use, whether you have to use induction or strong induction, if you always use strong induction, that will work. If you can use induction. But we use induction because this is, if you only need this, if you use all of this, it will take more time. So that's why we just use induction when we can use induction only. But otherwise, sometimes we want to use not only this, but also the previous things. I'm going to show you an example that will be clear. By the way, is it clear to you that these two are enough to say that they are all true? Yes, because in induction, if this is true and then inductive step is proved, you say that, okay, because of this, we know that this is also true. Because of this is also true, etc. But here, it's the same, because let me erase this thing. We assume that this is true, right? And because of this induction step, because of this, this is true. And because of these two, this is also true. Because of these two, three, the next one is true, etc. Because of all of this is true. And because of all of this is true. So it's still the same that all integers are covered. So these two inductions are in fact equivalent. So we can use anything that you would like to use. So let me give you an example of a strong induction that may not be used using just induction. Show that postage of 4 cents or more can be achieved by using 2 cent and 5 cent stamps only. This is a statement that we want to show. So what does it mean? So if you want to send a postcard to your friends, or for instance, then you will need to put some stamps here. And suppose that you need to have like 14 cents. You need to put 14 cents amount. You need to put stamps whose total amount is 14. And there are only two kinds of stamps available: 2 cent stamp or 5 cent stamp. Can you make 14 out of this? There are sufficiently many stamps of each kind. Can you make 14 out of 2 and 5? Yes. There are many ways, but you use 2 stamps twice, and 2 cent stamps twice, and 5 cent stamp twice. Then you will get this. And the statement says that this is always the case, as long as your stamp is at least 4. Your amount is at least 4. 4, 5, 6, any of these can be written like this. That's the statement we want to show. This is a statement involving n, right? So we can use induction. So let's prove this using induction. Induction on n cent stamps. Or n cent stamps. Postage. We get the total amount n greater than or equal to 4. Basis step. N equals 4. Can you write 4 using 2s and 5s? Yes. 2 times 2. You don't need 5s, so this is okay. True. I'm going to consider the next one as well. Why? Because we have to do that. I'm going to tell you later, but yeah. This is fine, right? 5 can be achieved using 2s and 5s, right? You will see why I did this. Now, inductive step. Suppose that k sent, k stamp, let's just k can be, let's say, just simply done for all k less than or equal to 4 and n. For n greater than or equal to 6. We have already covered 4 and 5, right? So we want to show that this can continue 6, 5, 6, 7, 8, etc. So let's assume that this inductive step. That means for any k sent postage, that can be written in this way, 2 as a sum of 2s and 5s. We want to show that n can also be achieved that way. Is this clear to you? Any question? Is this clear what I'm doing? Yeah, you can ask questions if it's not clear. Okay, let's see more. Now we want to show that, because here we assume that 4, 5, 6, up to n-1, they are all okay. We want to show that n is also okay. If you can show this by induction, strong induction, we are done. So let's do that. Since 4 is less, now we want to cover n as a sum. We want to write n as a sum of 2s and 5s, right? That's what we want. So let's just consider n-2. n-2 is, because n is at least 6, n-2 is between, obviously less than n. n-2 is between 4 and n, right? Because n is at least 6. Because of this, by induction hypothesis, we can write n-2 as a sum of 2s, so 2 times a times 2 plus b times 5. Because we assume that any integer between 4 and n can be written in this way. So a, b are integers, positive integers or non-negative integers, like that. Now what is n then? You just add 2 to this number. So it's going to be a plus 1 times 2 plus b times 5. Okay? This means n can be achieved as well. So the inductive step was has been proved. So by induction, it's true for all n. The statement is true for all n greater than or equal to 4. This is an example of a strong induction. Here we didn't use n-1. That's why we used strong induction. If you use induction, you cannot say that this is this. You cannot assume this because we only have we want to go from n-1 to n. But here we went from n-2 to n. So that's why we use a strong induction. Is this fine or? And because of this, we needed to have two things, because 4 is not enough. Because if n equals 5, n-3, if n equals 5, n-2 will be 3, which is out of this bound. That's why I consider two things. So sometimes you want to check several things in your base case, in your basis step, not just the first one, but the second one or the third one, sufficiently enough things that you can continue your inductive argument. Sometimes you need to have more. depending on the problem that you are solving. Is this difficult or okay? Can we move on to the next, or ask me some questions if you have any? Yeah, you need some practice to do this. Yeah, so there will be some homework problems this week, so I'm going to tell you more later. All right. Now, well-ordering property. So the well-ordering property says the following: every non-empty set of non-negative integers has a least element, the smallest among all of them. So you have a set, non-empty set of non-negative. If it's finite, then it's of course true. But even for infinite set, this is true. So in fact, this is equivalent to induction. So well-ordering property is equivalent to induction. So sometimes you can use well-ordering property. But by the way, is this clear? So for instance, let me give you some example. Let's say A equals, 1, 2, 3, dot, 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 this. This is an infinite set. There are infinitely many integers. But is there a least element? Is there a small least element here among all of this? Yes, has a least element. What is that? What is the least element of this set? 1. So well-ordering means, literally means you can order your set well enough. You can put the smallest element in front, and you can put the next smallest, the second in this way. You can list your set in this increasing order. So not all sets have this property. For instance, if Z, is there a least element of this set? Doesn't have any least element. Minus 100, there is a smaller element than that. Minus 1 million, there is still a smaller element than that. So it has no least element. But this is okay, because it's not in this assumption. It doesn't satisfy this assumption. Doesn't say that all elements, all sets satisfy this. If this set, all the elements are non-negative, then it has a least element. Because there are negative integers may not have least element. Also, the important part here are these two things, non-negative and integers. For instance, example, if A equals this set, 0 to 1, which means set of all real numbers x such that x is between less than 0 and 1, doesn't have a least element, no least element. What is the least element if there is? 0.0001, there is a smaller element than that, so no least element. So it is important that this integers non-negative. But as long as your set has only non-negative integers, there must be a least element. Okay. This is very useful to prove a theorem like this. Theorem. It's called quotient remainder theorem. So this is a very simple fact, and you all are aware of this statement. But yeah, the proof of this is not completely obvious. So if d and are integers and d positive and maybe negative, doesn't matter, then there exist unique integers q and r such that n is equal to d times q plus r, and r is between 0 greater than or equal to 0 less than d. Okay? So this is a very simple fact that we all know this is what this is. So that means we can always divide a number by a positive number, or integer by a positive integer. For instance, 17, let's say n equals 17, d equals 3. 17 can be written this way: 3 times 5 plus 2, right? 2 is between 0, could be 0, and less than 3. You can always write, you can always find d and r, q and r. And usually q is called the quotient, r is called the remainder. So whenever you have two numbers, n and d positive, they are both integers, you can always divide n by d, and you have a remainder which is between this. Okay? And it says two things basically: the existence of these two numbers, but also uniqueness of this. That means, so in the previous example, 5 times 2 plus 3 plus 2. This is the only way to write 7 in this way. Can you write in a different way? You cannot. Maybe you can try to write this way, 5, but this is not in this range. If you want this to be in this range, this is the only way you can write 17 this way. This is, yeah, you all know this fact, but how can you prove this? Well-ordering property can be used to prove this. Okay, so let's say X is this set, n minus dk, where n minus dk is positive and k is an integer. So we just consider one set. Okay, considering this set is the difficult part, but yeah, let's consider this. Sometimes proof is not always obvious, but once you have it, you can understand that. So let's consider this set. Is this a non-negative set? I mean, a non-empty set? So we want to use well-ordering property on this set. In order to do that, we need to show two things: non-empty, and all integers, all elements are non-negative integers. So first, is this non-empty? It is of integer of this form for all integers k. Is this non-negative? Let's think about this. Yes, it is non-negative because yeah, I think I should have said this, but Okay, actually it doesn't really matter, but we can do this. But let's assume n is also non-negative. Even if n is positive, n is negative, you can do this by taking k to be very small. But just for simplicity, then n is in x, right? Because n equals n times d right? It is in x. So x is not empty. Is this fine? Now what about are all integers, are all elements in x non-negative integers? Yes, because we are only taking non-negative integers of this form. So x is a non-empty, empty set of non-negative integers. So we can apply the well-ordering property to this set. Okay. So x by the well-ordering property, x has a least element. Say just r. Let's say the r is the least element because it has a least element. Okay. Then because this is an element here, we have n equals d times q plus r. Why? Because r can be written, I should be written in this way. R equals n times n minus dk. If you move this to the other side, let's just say k equals q, then we have this. If you move this to the other side, you will get this r. Is this fine? Okay. Okay. So r is positive, not negative, because r is an element in x. Now what? If we want to show that r is less than d. If r is bigger than d, we can find a contradiction. If r is, suppose that r is greater than or equal to d, and see what happens. Then n minus, say r minus d. What is r minus d? R equals n minus dq. So n minus dq minus q. No, d. So r n minus, yeah, this is r, so it's r minus d. And what is this? N minus d times q plus 1. And it is of this form, n minus dk. And is this positive, non-negative? It is non-negative. Okay, let's do it this way. Since we assume, because of this assumption, r minus d is positive, non-negative, of course. That means r minus d is an element of x. What is this? This is a contradiction. R minus d is greater than or equal to 0 and less than r because we subtract d. D is positive. And r minus d is x. What can you say? What is, so we have contradiction to what? What is r? Yeah, r is the smallest element in x, but this one is smaller than r. Contradiction. To the minimality of r. That means this assumption was wrong. Thus, r must be less than d. And we know that r is greater than or equal to 0. So we have found such an example, n equals dq plus r with this. So we have shown that there is an integer r and there is an integer q satisfying this, the condition. Yeah, this may be a little difficult if you look at this for the first time, but this is a very good example of using well-ordering property. But actually, proof is not yet done. We have to show one more thing. What's that? Because the statement says two things. They exist and they are unique. You cannot find other examples of this other than this R and Q. Okay, I'm going to move on to the next page. So to show the uniqueness of Q and R, suppose that n can be written in a different way, d times q1 plus r1, where r1 is, all right? Suppose this way. And if you can show that q1 is indeed equal to q, r1 is indeed equal to r, then they must be unique. There is only one way. No matter how you pick this, they always end up getting the same thing, then they must be the same. There is a unique thing. So let's consider r minus r minus r equals r minus r1. We know, okay, let's write. Yeah, we assume two things. Oops. Right? Let's take their difference, r minus r1. r1 equals n minus dq1 for this, make minus dq. What is this? We can cancel this n, and it's going to be d times q minus q1. Okay? But what is r and r minus r1? What is the range for r minus r1? What is the maximum value for this? It must be less than d, right? R1 is less than, r is less than d. We subtract something non-negative, still less than d. And must be greater than d, minus d. Because if you want this to be the smallest, this is 0, this is d minus 1. So this must be in this way. Is this fine? Now, what does this say? This says r minus 1 equals, this is a multiple of d. So d times L integer. Because, you know, this is L. All right, so here, d times L between minus d and d, what is L? Divide everything by d, we get this. L is an integer, 0 is the only integer. That means this is 0. R equals R1. So if you plug in there, Q must be equal to Q1. So they are unique. R, Q are unique. You cannot find anything else. They must be the same. So this is the end of the proof. Yeah, so proofs are very important in mathematics and also in this semester. So if these are not really, if you're not very comfortable with these kind of things, you need to solve some problems. So tonight,